Assalamu alaikum dear students, we're back with another video lesson. In the previous video lesson, we were talking about the types of motion that we're going to deal in this chapter. So we were talking about translational motion and rotational motion. In translational motion, we said objects are changing their location or position, while in rotational motion, objects were not changing their location, they were just spinning. We said for translational motion, there were linear motion where objects move in a straight line, and then there were circular motion where objects in a circular motion. The reason why we categorize them under translational because in these two cases, objects are changing their location. While in rotational motion, objects were just spinning, like the motion of the Ferris wheel, let's say, the wheel was just spinning or rotating without changing its location. But we said if we take the motion of one seat, then you will notice that the motion of that one seat, it is undergoing circular motion. So of course we said that whenever there is rotational motion, there is always circular motion too. And then after that, we've learned how to measure the distance traveled by an object in a circle. We said we cannot just measure the distance traveled, let's say, just like in grade 11. So what do we do instead? We'll measure the angle that is covered by the object. And how do we measure the angle? We'll say, we had an equation. We said to measure the angle, we'll say arc length divided by the radius here. And then we also said that if the arc length, the distance traveled on the edge, if it is equal to the radius, then we get an angle. Its magnitude is 1. And we said we also said that we'll use radian to measure the angle theta. So if the arc length it is equal to the radius, the angle we get it is just 1 radian, which is, we've also learned that 1 radian it is approximately equal to 57.3 degrees, which is also about 0.16 revs here. Don't forget these. And we also learned how to convert, let's say, from one angle to another, because angles can be measured in radian, can be measured in revs, or can be even measured in degrees. Today we'll talk about something not that different from what we have learned before, but of course we have a different title, you can say, and that is angular displacement. What do we mean by angular displacement? If you remember in grade 11, we had displacement. So this year, of course, we have angular displacement instead. So let me give you an example here. Once again, if an object were going from point A to point B, was traveling some displacement here. But because we're dealing with angles this here, so, or when objects are moving in a circle, so the angle is changing here. This is, you do know that that is the axis of rotation here. So if an object is going from point A, let's say, to point B, of course it is going to cover an angle here. What about if it is going, let's say, from, let's say, it keeps traveling, let's say, now from point B, let's say, it might go to point C at some point here. So now, of course, this angle is going to change here. So now, if I ever wonder, for example, or if I want to know what is the angle covered from B to C, then of course you can see that there is a change in the angle. Let's just call this one 1 and call this one 2. So this change in the angle that is covered, that is what we call it angular displacement. So here now, that is basically what we're going to use in grade 12 this year here. So we'll measure the angle that is covered by the object, and you already learned how we can do that. But let me tell you this. This is the equation now. Instead of just using theta, we'll say the change in the angle theta. Now hereafter, we're just going to call this one angular displacement. Angular displacement, and that is of course still measured in radian, don't forget. So how do we do that? Now, if an object is going from point A to point B, that is of course an arc length, you can call it 1. If it is going from point B to C, that is another arc length here. So can we say there is a change in the arc length as well if we're ever going to measure, let's say, the angle that is covered when it goes from point A to point B? Yes, and in this case we can say there is a change in the arc length, that is the equation that we have, divided by the radius. So whatever the numbers are, it is going to be in radian, because these are both measured in meter and meter, and still they cancel out. So we'll use radian to describe the angle or the change in the angle that is covered by the object. But you don't have to worry about the details here. Now, whenever you want to talk about angular displacement, all you have to do, you can say this. If this is, let's say the radius, that is point A, and this is point B here. So you could just say this angle here, right, can be found by knowing the arc length here, or the change in the arc length divided by the radius. So you don't have to go through the detail if it goes from point A to point C to point B and then to point C and all that. And that is the equation. The change in the angle, or delta theta, that is change in the arc length divided by the radius. That is the angular displacement that we have. All right, so how can we define angular displacement? Well, we can say angular displacement, it is, how about if we just say it is the angle that is covered by an object. Let's say it could be a point or a line when it is rotating about some specified, let's say, axis, and of course in a specified, you can say, direction as well. Okay, so once again, angular displacement, it is the angle that is covered by an object, could be a point, could be even a line that is rotating, we can say, in a specified direction, and I'll tell you what I mean by that, and of course around the specified axis as well. When it comes to angular displacement, it is a vector quantity. And what do we mean by vector quantity here? But before that, let me not forget, there is another definition for that. Can I also say it is the ratio? You do know that in physics, when something is divided by something, we can say the ratio. Can I also say the ratio of the arc length to the radius? That is also could be used as a definition here for the angular displacement as well here, even though it might not be that popular, but it still can be used as a definition as well. Now this angular displacement here, it is a vector quantity. What do we mean by vector quantity? That means it has both magnitude and direction. It has both magnitude and direction. Now, regarding the magnitude, we can use the equation to find what is the magnitude of this angular displacement here, that is, change the arc length divided by the radius. This is how we can find the magnitude, the value for the angular displacement here. But regarding the direction, now at this point, of course, we can have two directions here. If an object is moving the same as a clock, we can call it clockwise here. So for example, we know that this is 12, 3, 6, and 9. If it is going to rotate this way, we're going to call this motion here clockwise. All right, let's get it back. Clockwise. All right, clockwise rotation, you can say. Hereafter, I might just write CW, that is for clockwise rotation here. What about if it is going opposite to the motion of a clock? Then, of course, we can call this one counterclockwise rotation here. So, but at this point, so for example, what would be the difference if it is clockwise or counterclockwise? Then we'll say if the motion is, or the direction of the motion is clockwise, we can say the arc length that is covered, it is going to be negative. Then delta theta also is going to be negative as well. But when are they negative? If the rotation is clockwise. How about if the rotation is counterclockwise? Then we can say the arc length, it is going to be positive. Also delta theta, it is going to be positive as well. That is, for now, all what you need to know regarding the angular displacement. I'll repeat this again. Angular displacement, it is the angle that is covered by an object, a point, or a line that is moving in a specified direction. This is what we mean by a specified direction, because the direction is either going to be clockwise or counterclockwise direction here. Okay, and then of course around a specified axis, which is going to be the center or the axis of rotation here. Okay, now at this point here, and also remember this, that's pretty much what we need to know here. And then there is something here which I would like to tell you at the end or later, like what if they did not talk about the direction here? Then of course we'll just consider it positive here. Okay, now once again, angular displacement, it is the angle through which a point, a line, or a body is rotated in a specified direction about a specified axis, or we can say it is a ratio of the change in arc length divided by the radius here. Angular displacement is a vector quantity, we said it, and in some books you might see this, you might say it is direction is determined by using the right-hand rule. What is exactly the right-hand rule? You don't need the details at this point here. Just remember this. If it is clockwise, it is negative. Counterclockwise, it is positive. But let me just give you an idea. What if it is what is the right-hand rule, even though you might not need it? If an object is moving, let's say, counterclockwise, let's say. So let's say an object is moving from point A to point B here. So if I use my right-hand rule here, and if I, let's say, align my fingers, the 4 fingers, in the direction of the motion, you can see that my thumb is pointing upward. So this is what we use in order or to determine, let's say, whether angular displacement is positive or negative. The forefinger will be in the direction of the arc length, and then your thumb would be in the direction of the angular displacement. And what do we mean that? Or does that mean these two are perpendicular to one another? No. If it is going to, for example, if you do this, your thumb is pointing outward. And we know that if something is pointing outward, that is considered as positive. This is why we say if the rotation is counterclockwise, delta or angular displacement is positive. But what if the rotation is counterclockwise, like opposite to this one here? Then you would notice that you can see that your thumb is going to point inward here. And we know that if something is pointing inward, or it's going to, that is considered as reducing here. And then we can consider that as a negative. All right, this is why, again, if it is clockwise, it is considered negative. If it is counterclockwise, it is positive. Once again, this is might be something that you don't need to. Just think of this one. If the rotation is clockwise, clockwise arc length and delta angular displacement are negative, but if the rotation is counterclockwise, then the arc length and angular displacement are both considered positive here. Okay, and this is the equation that we use for delta or angular displacement. We said it is equal to the change in the arc length divided by the radius here. And remember these study tips. This is one thing that we've mentioned earlier. We said radian is a pure number with no dimension. It is just a ratio of the change of arc length divided by the radius. That is first. And we also said that both the delta theta and arc length are considered positive if the rotation is counterclockwise. They are considered negative if the rotation is clockwise, and you can see where it is. But there's one thing I haven't mentioned, and that is the radius. The radius, since it is a scalar, it is always positive. Okay, so we know that if this is the radius, because it doesn't matter which direction you're taking this one, because radius is a scalar, so it is always positive, can never be negative. Don't forget this. All right, now let's solve a few questions and see how it is done. Let's say, remember this, whenever it says something is rotating clockwise, we said that the arc length and angular displacement are both going to be considered negative. And that is when, if the rotation is clockwise. So we have a question, says what? It says, Shahzad rides on a cursor that is rotating clockwise. If it is rotating clockwise, we said that arc length is going to be negative. Delta theta is also going to be negative. Don't forget this. Then he travels through an arc of length, or an arc length of 11.5 meter. Now remember this, because the rotation is clockwise here. So this is the arc length. It's telling you this is the arc length, the delta S. Let's change this color here. Okay, so this is the arc length, but remember it is going to be negative 11.5. Once again, why? Because it says the rotation is clockwise. Now, if the angular displacement is 165 degrees here. Now, remember in the first session, I told you about a study tip. We said that angular displacement, or the angle theta, right, can be measured in radian, in revs, or even in degrees. But now hereafter, we're going to use theta in calculations. If it is not in radian, you have to convert to radian before you use them in calculations, because we don't use the other angles here. All right, so remember this, which means in this case, we have to convert this angle theta from degrees to radian. Don't forget. And we're going to see how we can convert this one here. So the question says, what is the radius of the cursor here? Okay, so since we have delta theta, we have the arc length, and they're asking for the angular, the radius, sorry. So we can write this equation. Delta theta, that is the angular displacement, it is equal to the arc length divided by the radius. True? Now, if you want to find the radius, we can simply rearrange the equation, yes? Or you can cross multiply and do whatever. Since these two are in the same line, we could just swap them here or switch them. So radius, it is equal to arc length divided by delta theta. But wait a minute, don't just do numbers here. Okay, you need some conversions. Okay, so before we do that, we said delta theta cannot be used in degrees. So how do we convert degrees to radian? We've learned two methods, okay? So I'll do them both. 100, by the way, since it is clockwise, it is negative 165 degrees, all right? We can multiply by, remember, degrees down, radian up. Do you remember the number beside each of those? For radian, it was 2 pi. For degrees, it was 360. Now, of course, degrees and degrees cancel out. So 165 times 2 pi divided by 360. And then, of course, you get the answer in radian, which is going to be negative 2.88 radian. That is one method to do that. And, of course, you can do the second method, which is way easier. 165, remember, degrees. If you want to convert degrees to radian, you could just divide by 57.3 degrees. And once you do this, of course, you get, again, this is negative because it is clockwise, so negative 2.88 radian. Now, all you have to do, just plug in the number into the equations here. Okay, one more time. So the arc length was negative 11.5. Why was it negative? That is because the rotation was clockwise, and then divided by negative 2.88, and then of course you can find the radius, which is going to be 3.99, and that is going to be in meter. Remember, if at any point you get a negative value, redo your math because you've done something wrong. We said radius, it is always positive. Okay, now that is regarding the first question here. Okay, let's see if we can try this. Try this question too. There is another easy question. It says what? A beetle sits on top of a bicycle wheel. Okay. A beetle sits on top of a bicycle wheel and flies away just before it would be squashed. Okay. Assuming that the wheel turns clockwise again, whenever it says clockwise, arc length is going to be negative. Delta theta is also negative. The beetle's angular displacement, so they'll give you the angular displacement this time. It is pi radian, but remember, since it says clockwise, again, negative pi radian, which corresponds to an arc of length. So this is the arc length. Once again, because it is clockwise, so negative 1.2 meter, what is the wheel's radius? Again, the radius is unknown. So all you have to do, just do the same math, and of course you can find the answer. But do I need any conversion this time? No, because the angle is already given in radian. So once again, delta theta, it is equal to the arc length, that is delta s divided by the radius. We want the radius, so rearrange the equation. We can say the radius is equal to arc length divided by delta theta. But once again, because the rotation is clockwise, so the arc length is going to be negative 1.2. Delta theta is going to be negative pi radian. Once you divide the two, see, negative cancels out. So the radius is going to be, or it is equal to 0.38 meter. This is how you can do that. Very simple, very easy. And make sure you practice a lot so you know how you can solve questions like this. Okay, now at this point, take a look. We have a few questions. Sometimes those added questions are exactly the same. Sometimes there are a few changes where you can say they might just change one or two numbers, but the question is still the same and it can be solved the same way as well. So there's a Wazadi question, says a beetle sits on top or at the top of a bicycle wheel, assuming that the wheel turns clockwise. So once again, delta s, it is negative, delta theta, that is the arc length, delta theta, the angular displacement, must also be negative. The question says, what is the beetle's angular displacement this time? If angular displacement, which corresponds to an arc of length that is 1.2. So remember, when it says an arc length is going to be negative because the rotation is clockwise, and the wheel's radius is 40 centimeter. Don't forget, we were not allowed to, or you have to convert centimeter to meter before doing the calculation. So if I want to solve this question here, we can say the question says find the angular displacement, that is the arc length divided by the radius. Once again, okay, what is the arc length? Because the rotation is clockwise, so it is going to be negative 1.2 divided by the radius. But how do we like convert centimeter to meter? You just simply divide by 100. That would equal to 0.4 meter. You might say, Mr., why don't you write the negative? Remember, radius can now be negative. So now, once again, delta theta, that is equal to 1.2 divided by 0.4. What is the answer? Let's get a calculator. By the way, don't do mental math in Inuizati, because that is basically you're trying to get as many marks as possible. So try not to ruin that or lose that 2 marks in here. So negative 1.2 divided by 0.4, the answer is going to be negative 3. Don't forget, negative 3 what? Negative 3 radian. Now see the options if you have this answer there. Okay, that is interesting. Now, this is the answer that I have. Look, this is 0.3, which is not in there. Okay, this is 30 radian, that is not in there, not the answer. And clearly it is not negative 0.3, so what do I need to do? There is another option here, but this one is in Riv, so what can I do at this case here? That's a very good question, right? So in this case, if the answer that I found, it is not in the options, and then there is 1 Riv in the question, is that an indication to tell me convert negative 3 radian to rivs? Well, perhaps yes. And that is actually. So how do we convert negative 3 radian to rivs? Okay, well, there are 2 ways, but the easiest or the fastest, just divide by 2 pi. All right, let me do the other way because I used that method, so we'll keep using that for a moment here. So negative 3 radian, radian should be below, and then riv up. Remember, there is 1 riv, and then here for the radian, that is 2 pi, yes? Radian and radian cancels out, so negative 3 divided by 2 pi. Let's do that. Divided by 2 pi. And the answer is going to be negative 0.477. Once again, negative 0.477 revs. Do we have this in the option? Yes, so the answer is going to be option B at this point. Okay, now there are, you might see, like if you go through this pamphlet, you might see some of the questions with a blue tag here. These are basically my questions, all right? And then regarding this, maybe some of the numbers that I'm using, it might, practically make sense, but some of them practically might not make sense. These are just for the sake of the question here. So we have a question that says an angle measures 7 pi over 3 radians. How many complete revolutions and additional degrees does this represent? And of course, if you try this simply, like this 7 pi over 3 radian, how many rivs does that equal to? All right, beside, maybe there will be an incomplete riv, okay? So what would be that incomplete riv in degrees? But I'll tell you something very easy. You can do that at any point without making any mistakes. Do you remember in the other lesson I told you, whenever you have fractions, always convert that to a number, to a digit, so that you can clearly tell which one it is. You can do the same procedure here. Now, when we have, wouldn't it be easier if I convert all this to one thing here? For example, when we say 1 riv, isn't that 360 degrees? Well, yes, well done. And then plus 120 degree. Would it be the answer in that case? All right, well, 360 plus 120, that is going to be 480. Is that true? 400, we can say this is about 480 degrees. Yes, that's one thing. Second, what about this one? 1 riv and 360. 1 riv is clearly 360 plus 60 degree. Isn't that 420 degrees? Yes. And of course, now you can continue doing the other 2 options here. And then the next thing, wouldn't it be easier now if I just convert this radians into degrees? Whichever give me the same degree, that'll be the correct answer. Now, how do you convert radians to degrees? Simply just multiply by 57.3, then you will get one of the answers, and then of course that'll be the correct answer. So what is the key to solve this one real quick? Try to convert all this into one thing. You can convert this, let's say, you can even convert this one to Riv if you want to, but that might complicate it a little. So it's best to, like in my opinion, it's best to convert all this into degrees and then just convert radians to degrees, which would be easier, and then you can easily get the answer right. Okay. Now there is more, of course, to practice, and that is practice A says what? Fill in the unknown quantities in the following table. Now, perhaps if you've seen those ADDIE questions, you will see like questions like this a lot, all right? Maybe if not in every single exam, of course, it is one, for example, maybe there will be, like questions like this in every at least let's say 2 exams in a row, let's say, or maybe let's say if not in one exam, it's going to be in the other exam, definitely. So how do we solve questions like this? I also consider these tables actually as a bonus mark. So that is just for you to grab the 2 marks and then move on to the next question. So you can see that here's delta theta, arc length, and the radius here. This one says find the delta theta in radians. So how do we do that? We've learned that for this one, delta theta, it is equal to the arc length divided by the radius. So what is the arc length here? It is 0.25 divided by the radius, which is 0.1. Then what would be the answer in this case? Of course, you could just say the answer is going to be what? It is going to be 2.5. 2.5 what? It is going to be radian. 2.5 radian, because they want the angle theta here. What about the second one here? This time they need the arc length here. So this is the equation. That is the arc length divided by the radius. How do you find the arc length? Just cross multiply, yes? So arc length, it is equal to delta theta times the radius. So you have delta theta, which is 0.75 radian, and then you have the radius, which is 0.5. Just do the math, you'll find the arc length, and the unit is going to be in meter. What about the third one? The third one is a bit interesting. Why? Because angle theta, or angular displacement, it is given, they want the answer in degrees. So how are you going to do that? Remember, we said the only angular displacement you're allowed to, like as a number, to use in calculations, that has to be in radian. And we can say the same thing when we get, or when we find the angular displacement. Whenever you find angular displacement, it is always in radians, don't forget. So if we want, or if the question wants us to find the angle in degree, after you find the delta theta, then you have to convert into degrees. So let's give it a try. And then this is what we have. Once again, let's just use a bigger space, maybe delta theta, it is equal to the arc length divided by the radius. What is the arc length here? It is negative 4.2. Negative 4.2 meter. What about the radius? It is 0.75. So what is the angle that we're going to get? Of course, we will get about, let's say, negative 5.6 radians. But that is not the answer we want, or the question wants, because it says find angular displacement in degrees. This is in radians. So now it is easy to convert. How do you convert radian to degrees? We've learned that whatever the angle in radian, that is negative 5.6, just multiply by 57.3, yes? And then, of course, you're going to get about 300, or negative, let's say, 321 degrees here. You can write degrees like this, or you can just write this small circle here, and that'll be the answer to this question. So what is the key to solve this question? First, find the delta theta, the angular displacement, and then after you do that, convert the angle from radian to degrees just by multiplying by 57.3 degrees. Okay, what about the third one here, or part D here? That is also interesting, so let's solve this one too. All right, for part D here, it says find what? Find the radius. But if you've noticed, this angle is given in degrees. And can we use degrees in calculations? We've just said that we're not allowed to, or we can't use degrees in calculations. So first we'll have to convert that into radian. Then after that we can get the number, or like do the math there. So once again, delta theta, it is equal to arc length divided by the radius. If you want to find the radius, it is equal to arc length divided by arc length, arc length. Okay, that is the radius, and then arc length divided by delta theta here. Once again, what is the arc length? It is positive 2.6. Okay, and then divide by delta theta. But once again, delta theta, it is in degrees. Can I use degrees in calculations? The answer is no. So how do you find, or how do you convert degrees? Let me do it here, let's say. Let's just leave some space here. So delta theta, it is 135 degrees. We're not allowed to use this in calculation, so we have to convert. But do you remember how do we convert degrees to radian? We simply divide by what? Divide by 57.3. So let me write it this way. We simply divide by 57.3 degrees. Then once you do the math, of course, you will get about 2.36 radians. Now, after you get this one here, now you can simply just plug in the numbers here, 2.36. Do the math, you will find the radius, which is going to be about 1.1 meter. That is how you can do that. It's pretty simple. I'm sure you all understand how you can do this. And if you're not sure, keep practicing until you fully understand how to do this. Once again, these are very easy. You can always get the 2 marks here. Now, there are Wazadi questions here, which is very similar to, it is exactly the same as the one we just solved, right? Sometimes numbers are different, as you can tell here. Sometimes even the same numbers are given here as well. So as you can see here, 135, that is 2.6, 2.6. So find the radius here. Okay, so this is sometimes you might see something like this. So this is basically the same as a table here, what is given. So these are what is given here. So only the radius is unknown, find the radius. See how many times it's been in Wazadi? So of course, expect questions like this. And then you can see this one too. Here says the unknown quantity in the corresponding table, that is equal to what? But once again, okay, they want the angle theta in degrees here. So delta theta, it is equal to arc length divided by the radius. That is negative 4.2 divided by 0.75. And find the answer. That is going to be in radian. Then after that, you just have to convert radian to degrees by multiplying whatever the answer is, 57.3, and then you will get the answer in degrees, and then it will be one of those. Then you could just do the number. But let me not forget here, this is negative, so of course this answer is going to be negative, so you will have to choose a negative number. All right, there's another question here. There is one thing I would like you to notice here as well. If you take a look at the question, would you just take a look and read it for yourself? It says a car on a Ferris wheel has an angular displacement of this much. So can I say this number is the angular displacement? Because that is in radian, and that's what it tells you. All right, if the car moves through an arc of length, what is the arc length here? That is delta S is going to be 12 meter. What is the radius of the Ferris wheel? Have you noticed something? Do they say the rotation is clockwise or counterclockwise? No. So what do we do in this case? We'll just pretend we didn't hear that, okay? So we'll just keep it positive. So remember this. If the question doesn't mention clockwise or counterclockwise, especially clockwise, let's say, we'll always keep the numbers positive so that less requirement, less headache, you could say. All right, so how do we do this one? So once again, delta theta, that is equal to the arc length divided by the radius. And they're asking for the radius, that is arc length divided by delta theta. Do we have to convert anything? No, because this one is given in radian, and the arc length is clearly in meters, so there's no conversion. 12 divided by 0.34, so the answer is going to be 35.3 is going to be in meter, and that's it. Simple enough. All right. Now, the next thing that we have is this question, which is a bit interesting here. We have a wheel, right? Let's take a look at this question. It says, when a wheel is rotated through an angle of 35 degrees, so there is a wheel, this wheel is being rotated, where it is rotated 35 degrees. So this is delta theta, but remember this is in degrees. A point on the circumference travels through an arc of length of 2.5 meter here. When the wheel is rotated, so this is the same wheel we're talking about, it is rotated through an angle of 35 radian. That is the second time we rotate the wheel, and then there is the third time where we are going to rotate the wheel, but this time 35 revs. It says the same point travels through an arc of length, let's say of 145, and 9 times 10 to the power 2, respectively. What does this word exactly mean? In physics, when we say respectively, that means the number comes in order. So this first number that here, it comes for the first angle that is mentioned here. So 35 radian, that point travels 145 meter. And then, what is the second number? That is 9 times 10 to the power 2. That is, of course, comes for the second angle, which is 35 revs in here. This is what respectively means at this point. So let's solve this question together. But first, I would like to do that on the whiteboard here. So once again, we have a wheel, and I want you to focus on this one here. This wheel, when it is rotated, or you can say through 35 degrees. Let's say this is 35 degrees. Okay, there is a point. It is rotated. This angle is 35, let's say theta, and the arc length was 2.5 if I'm not mistaken. So let's just say theta was 35 degrees, and then the arc length, all right, was covered or traveled, the arc length, that was 2.5 meter. Let me just double check with this one. Okay, it was 2.5 meter. Okay, now then after that, the same wheel is rotated. The same wheel, it is rotated, but this time, okay, this time it is rotated, but how many times, like how much is it rotated? It is the same wheel, but this time it is going to be rotated 35 radian here. So same wheel, it is going to be rotated, but how much? 35 radian. Don't forget this. It could be, I don't know, like how many revs, but whatever. So now the second time it is rotated, now we can say delta theta, it is equal to, delta theta, it is equal to 35 radian, okay? And then once it is traveling 35, and then another time, let's not forget this, let's just do this one too. Then the other time that is rotated here, okay, it is going to be 35 revs. What do I mean by 35 revs? It is the same as if you rotate this one 35 times. That is 35 revs. Okay? That is how far or you can say how much this point is, or the circle is rotated here. So once again, now we can say delta theta, this time it is going to be 35 revs this time. But in order not to get confused between, let's say, the angle theta, we can give some numbers to this. We can say delta theta 1, arc length 1, delta theta 2, and delta theta 3. Do you remember the arc length that is, we said that is covered by the point if it is rotated 35 times? We said it was, the arc length was 145. It was meters. I'll double check this number in a second, if I remember correctly. And then the third time it was the arc length that is traveled. Let's make this one the second arc length, and this is the third arc length. It was 9 times 10 to the power 2. You could just say 900 meters here. Okay, under 45, let's just double check this real quick. Okay, it was 145. Yes, it is correct. All right, going back to this one. So here's the question, says, what is the radius of the wheel? Let me ask you a question. Isn't this the same wheel that is being rotated? Well done. Yes, it is the same wheel. So does it matter if I use delta theta and this arc length to find the radius, or this information, or this one here? Shouldn't it all give me the same thing? Because the radius of the wheel is the same wheel, so it should be the same in every single cases. Well done. But at that point here, which one would be the easiest to calculate? It would be this one here. Why is this? Because this one is given in radian and this is in meters, so no conversion needed. Like the numbers are ready just to be used so we can find the radius. And then of course later we'll find the radius using this and that, just to confirm that it is the same thing here. Okay, so let's find, let's say, the radius in both cases here. So once again, delta theta, it is equal to the arc length divided by the radius. And if you've noticed, it says, like, it doesn't talk about the direction, so we always keep it positive. So if we want to find the radius, that is the arc length divided by delta theta. And then what is the arc length? It is 145 meters. What about the angle that is covered? It is 35 radian. And if you do the math, of course, you will get 4.1 meter. That is the radius of the wheel here. If I do the math here and there, will I get the same thing? You should. If not, there must be something wrong. Okay, so let's start with this one here. Okay, but first, can I use degrees in calculation? No. So how do I convert degrees to radian? Divide by 57.3. Well done. What do I get? Let's get a calculator. Okay. All right, so we'll say 35. It is 0 point something. I can't recall. So 35 divided by 57.3. The answer is going to be 0.6108 or whatever. We'll just use 0.61. And that is the angle in radian. Don't forget, in radian. Okay, now can I find the radius here? So once again, what is the radius? It is equal to the arc length divided by delta theta. That is going to be, the arc length is 2.5 divided by 0.61. Once again, you will get 4.1 meter. Okay, let's just double check. This is 2.5, don't forget. Divided by 0.61, the answer is 4.090 whatever, and that is, of course, we can say by rounding, it is still 4.1 meter. What about this one here? Of course, this must be the same as well, but first, can we use riv in calculations? No. We know that every riv, it is equal to 2 pi, so just 35 times 2 pi, we'll get a total of 70 pi's. That is going to be in radian. Now it is ready to be used in calculations. Okay, so once again, radius, it is equal to arc length divided by delta theta, right? What is the arc length now? It is 900 divided by 70 pi. And once you do the math, of course, you will get 4.1 meters. So you've noticed that doesn't matter which equation that for example, which delta theta angular displacement and the arc length I use, I'll always get the same thing. Once again, why? Because it is the same wheel, so the radius must be the same no matter what form of the angle you're using. All right, there's one more method you can do this to solve this question here, and that is, what is the other method? Now, we can find the radius also. If I say delta theta, it is equal to the arc length divide by what? Divide by the radius. Okay, that is basically the main equation. So let me just write, there's the arc length here, the arc length divided by the radius. So look, if I have, for example, if I want to find the radius, I can also use the total arc length that is traveled by the point divided by the total angle. But this angle, it has, all of them has to be in radian, don't forget. So if I do this, will I get the same answer? I should. Okay, it is like the total distance traveled, let's say, or the arc traveled by the point, and then divided by the angle that is being rotated, but totally, like in total. So now, for the arc, or total arc length, here at this point, the arc length was 2.5, plus here it was 145, and then here it was 900, yes? What about the angle? Here it was 0 point, it has to be in radian, don't forget, 61 plus, here it was 35, and then there was 70 pi. If you add all this together and then divide by this, don't forget if you're using a calculator, make sure you use bracket for the denominator numbers, and then you will again get 4.1 meter, which is the same as what we have gotten in each one of those here. So remember this in Wizari. Of course, this one been in Wizari, but there is one thing. It might just give you one of those, let's say, or let's say a point on the circumference travel this much, the angle that is covered is this much, it might be in degrees. And of course, they'll say, what is the radius? Then just convert the angle from degrees to radian, then radius arc length divided by the angular displacement, you can simply find the radius, and that'll be that simple. All right, I hope that was beneficial. All right, going back to next one, you can see that everything is written right here. All right, moving next. This is how if you want to, for example, do it all together. Now, you can see that this is the Wizard question. You can see that it says when a wheel is rotating through an angle of 35 degrees, remember you'll have to convert these degrees to radian by dividing by 57.3, then you will get the angle in radian. Right? It says a point on a circumference travel through an arc of length. So this is the arc length, this much. What is the radius of the wheel? So once again, the radius, it is equal to the arc length divided by the angle theta. The arc length is what? It is 2.5 divided by the angle. Remember, divide 35 by 57.3. We said you should get, was it 0.61 if I remember? Then you do the math, of course, you will find the answer. If not, you just double check with the numbers, then you will get the answer correctly. All right, now we have something else, and that is angular speed and the rate of rotation. What is exactly angular speed? And of course, everything you study this year, it is related up to this point, it is related to what you've studied last year. Do you remember how we used to calculate velocity last year? Okay, so we set velocity here. Once again, if an object goes from point A to another point, let's say it was covering a certain displacement over a certain time. So in order to find velocity, it was, let's say, point A to point B here. Okay, velocity was, or average velocity, we were saying displacement over the time here, and it was measured in meter per second. But again, that was last year, grade 11, and this is called translational motion, where objects move in a straight line. But because we're dealing with angles this year, so we have angular speed in this case. And you might say, Mr., why not angular velocity? Well, you can see that, for example, some sources, or let's say different books, of course, use different names for this. But the truth is this: when we say angular velocity, that is a vector quantity. But there are that is a vector quantity which has both magnitude and direction. But there are some books that still use angular speed, or kind of like, let's just say, makes no difference between angular speed and angular velocity. So from this our book, let's say it's one of them. It differentiates or makes no difference between angular speed and velocity. So we'll just keep saying angular speed, even though at some points we're going to use directions too. Normally in grade 11, we've learned that when we say angular speed, when we say speed, that means it has only magnitude. But this here, again, because we're dealing with angular stuff, so we can use angular speed, and at the same time, don't be surprised if we use direction too. Okay, so that is what we have. So this here, when objects move in a circle, we're going to use angles here, because that is what it is. Here's, let's say, that is the radius of a circle. A point or an object is going from, let's say, point A to point B. Of course, it is going to, let's say, cover some angle here. That is the angular displacement. But this motion or movement happens over some time, right? So how fast the object goes from point A, let's say, to point B, okay, moving in a circle, that is called angular velocity. So what is angular velocity exactly? We're using this letter to represent angular velocity. And that is a Greek letter, it's called omega. All right, don't forget this. That is not W. All right, this is W. This is omega. It is a Greek letter used to represent the angular velocity. Used to represent what? Angular, let's just say angular speed in this case here. Angular speed. All right, so what is the equation exactly? It is the angular displacement divided by the time here. So what is the unit for angular displacement? It is, we said earlier that delta theta is measured in radian, and now time is measured in second. So we'll say the unit for angular speed, it is radian per second. All right, remember this. Okay, now at this point, or for velocity, we can say, or angular speed at this case, let's say it is measured in radian per second. Angular speed is also a vector quantity. What do we mean by that? Okay, so that is, if the rotation vector quantity, that means it has both magnitude, right? Should have saved some space. It has both magnitude and direction. Okay, for the magnitude, of course, we use the equation and that's it. What about for the direction? The same as before. If an object is rotating clockwise, we said earlier that arc length is going to be negative, delta or angular displacement were negative. Now we'll add one more thing, and that is the angular speed is also going to be negative. But if the rotation is counterclockwise, that was clockwise, if the rotation is counterclockwise, arc length is going to be positive, and then angular displacement is going to be positive, and now angular speed is also going to be positive too. But what if they did not talk about the direction? We'll just consider them positive, and that's it. All right, now remember this, up to this point, we have, like we've learned regarding velocity, let's say. In grade 11, remember velocity was delta x over delta t, or displacement over the time it was measured in meter per second. But this year now, we're going to call it angular speed, and it is can be found using delta theta, because we're dealing with angles, angular displacement over the time it is measured in radian per second. Very good. Now that is all about angular speed, but up to this point, if you've noticed, we haven't defined angular speed here. So how do we define this? You can, well, there's one good thing, there's a good news actually regarding this. If you know or remember the equation, you can always use the equation to define or to remember the definition. Now here's one thing, we can say angular speed is normally describes the rate of rotation. In other words, it tells you how fast the rotation occurs, how fast the rotation takes place or happens. So once again, we can say angular speed, it is the rate at which a body rotates about an axis. That's one way to say. There's another way. Remember we said you can use the equation. In physics, whenever you hear the rate of, that means something is divided by the time. Whenever you hear the word the rate of, let's say, the rate of, that means something is divided by the time, or something divided by delta t. So regarding the angular speed, what can I say? I can say it is the rate of change of angular displacement. What does that mean? That means angular displacement divided by the time. So once again, the rate of something divided by the time. What is divided by the time? The change of, you know that this symbol delta, it means the change, the difference, right? Okay, so the change of angular displacement, it is measured in radian per second. So we don't use meter per second any longer because we're dealing with angles here. Okay, now there are a few things I would like you to know. Now this angular displacement, just like, angular speed in here, because we said the unit is radian per second, yes? And that is, so in other words, I can tell you that if angular speed is given in radian per second, that is the only thing that we're going to use in calculations. What if angular speed is not in radian per second? Because, and let's say it might be given in some other different units. It might be given, let's say, in revs per second. Could be revs per minute, let's say. Could be revs, let's say, per hour. Could be, and it goes on and on. It could be revs, let's say, per month, or even per day, or even per the year, let's say. But if it is ever given in these forms, we're going to convert them to radian per second so that we can use them in calculation. But is that the only thing? No. It can also be given in degrees, let's say, per second, and then degrees, let's say, per minute, could be per hour, per day, per month, or even per years. But no worries, this one is the least popular. It's mostly, let's say, radian per second. You might see a few times given rev per second, or per minute, let's say, but we can convert this into radian per second, then we can use them in calculations. But how do we convert them? All right, let's take the examples. Let's say we have an object, or let's say the angular speed of an object, it is given, let's just say it is 2 revs per second here, right? It would be best if you write this one actually like in a fraction here, just for example, something like this, 2 revs per second. Now here's the thing, do I need to change the second? No, only the rev, and we know that every rev it is equal to 2 pi radian now. So if I rewrite this one, that is going to be 2 times 2 pi, it is going to be multiplied or whatever, that is going to be radian per second. See, that is now what you have to do. And then 2 times 2 pi, that is going to be 4 pi radian per second. Do you see how it is done? I hope. And that is all of it. What if it is in different methods? Let's say another example, right? Let's say this is the first thing. What if it was, let's say, 2 revs, let's say per minute this time? Make sure you write it this way because it makes the conversion way easier. So once again, we'll just write what is given here the same. And then you might wonder if we can use the first method that we've used to convert angles. Absolutely yes. But this way is way easier at this point here. So we'll say 2. Remember, instead of, or every rev, it is equal to what? You can do it here as a matter of fact. Every rev, it is equal to 2 pi radian. And we know that every minute, it is equal to 60 seconds. And at this point, let me tell you this. We know that every minute, let's just separate this one. Every minute, it is equal to 60 seconds, yes? And then every hour, it is equal to 60 minutes and then times 60 seconds, but we don't do that. We'll just say it is equal to 3,600 seconds. What about 1 day, let's say? Okay, that is equal to 24 hours. Each hour it is 3,600 seconds. What if it is 1 year, let's say? When it comes to 1 year, of course, the question might tell you like how many days, or let's say a fraction of a day are in 1 year. The number that we use this year, it is always 365.25 days in a year. So how do you convert this to second if you ever need to? We'll say 365.25 days. Each day is, you say, 24 hours. Well done. Every hour it is 3,600 seconds, and that's it. So you do the math, you'll find how many seconds are in 1 year. But what you need well, actually, it's best to know all this so that you could do the math quickly or quick enough, let's say. So now at this point here, how do I convert this one more time? So that is going to be 2 times 2 pi divided by 60. That is going to be radian per second. Well done. Now you just got to do the math and simplify this. And that's it. Okay, what if it was, let's say, rev per hour? We'll do the same thing. It could be any number, by the way. Let's say this time 2 revs per, I don't know, you say that. Let's say per, I don't know, let's say 3 hours. Okay, or just hour, let's say, just 2 rev per hour. Okay, so now once again, let me just do it here again. So instead of, okay, so now every rev clearly is 2 pi. So you can just multiply by 2 pi radian. And then every hour is 3,600 seconds, and that's it. Or 3,600, makes no difference. So now you just got to do the math. That is going to be 4 pi's, okay, radian, divided by 3,600 seconds. So now we've converted from rev per hour to radian per second. There's one more conversion left, okay? And you might wonder how you can do that. What if it was, let's say, something like this? Let's say 300 degrees, let's just say this, degrees, let's say per minute. Let's just assume that, right? How do you convert this? Now this one is a bit different from the rest. So just write what is given the same. That is 300. And then do you remember how we convert degrees to radian? Okay, degrees to radian. We simply, like divide whatever it is, the degree by 57.3, then we'll get the answer in radian. Do you remember this? Okay, so if you want to convert 300 degrees to to radian, you just have to divide by 3. You just have to divide by 57.3. And then now you got radian here above, right? What about the minute here? We know that every minute it is equal to 60 seconds. So one more time, you have to divide by 60. So what happens here, there's another way to say or to write this one here, but I would recommend you do that each at a time here. So first, 300, convert this to radian, and then that is the radian per minute. Now just divide by, convert the minute to second. That would be easier. If not, you could just do that in one step. That is 300. If I divide or convert this to radian, I'll have to divide by 57.3. And then every minute it is equal to 60. So now you have to divide 300 by these two numbers. But I would recommend you try this one first because it might be less confusing for some of the, I'm sure that maybe, most of you get how to do that in one step, but in my opinion, this might be a bit safer at this point. All right, so let's get back to this. We said angular speed, remember the keywords. It is the rate at which a body rotates about an axis. That's for second. We said it is the time rate. Whenever you hear or see the time rate, that means something divided by the time. The time rate of what? Of change of angular displacement. Isn't that delta theta? So delta theta over delta t, that is angular speed here. Angular displacement is basically the time rate of change of angular displacement. That is angular speed, and it is usually expressed in radian per second. Sometimes they might even give you this, especially once it came in Uzadi, like it says, what is the time rate of change of angular displacement? And it is usually expressed in radian per second. So whenever you see radian per second, that is no doubt it is angular speed. Okay, so we said speed can be, like last year, it was delta x over delta t. Or you can say translational speed, but for angular speed, we'll use, or to find the average, let's say that is delta theta over delta t, angular displacement over the time here. Okay, and of course, this is measured in radian, this is second, so it is going to be radian per second. All right, now I hope you understood this well. We have a few study tips, and these are also very important. The first one says, angular speed describes, we've mentioned this earlier if you remember, angular speed describes how fast the rotation occurs, don't forget. So that is what do we mean by angular speed. And then second says angular speed can be given in radian per second, rev per minute, per hour, per days, per month, it doesn't matter. If it is not given in radian per second, they should be converted to radian per second before we use them in calculations. And then third one, it says angular velocity is a vector quantity. It has the same direction as the angular displacement. We've mentioned that if the rotation is clockwise, arc length is negative, right? Angular displacement is negative. Now angular speed is negative as well. But if the rotation is counterclockwise, these are going to be positive. And these are some of the conversions we've learned regarding how to convert, let's say, if it is not in radian per second. Okay, but then there is also, we've talked about this one as well, but there's one thing which is not mentioned here, and that is, what about the time? Can the time ever be negative? No, the time is always positive. So what are the things that are always positive up to this point? We said radius is always positive. Now the second thing that is always positive is going to be the time, or delta t. Okay, now see these Rosati questions, you can see that it is exactly the same as, like the definition here. And if, just in case, if you didn't remember the definition, it says the rate at which a body rotates, right? At which a body rotates clearly, okay? And then even if you didn't get this part, it says what? It is usually expressed in radian per second. What is this unit for? Isn't it angular speed? Yes, and that is angular speed, which is option B. What about this one here? It says it is the time rate of change of angular displacement. Do you remember we said whenever it says the time rate, that means something divided by the time? Yes. Change of what? Change of angular displacement. That is delta theta over delta t, and that is angular speed again. And that is option C. Well done. Now, do you remember the conversion here? We have a question says what? 420 revs per minute, it is equal to dash radian per second. So clearly they're asking us to convert rev per minute to radian per second. All right, get your calculator out. And then we said that every rev, it is what? Let me change this color. Okay, we said every rev, it is 2 pi radian, yes? And every minute is 60 seconds. Now do the math for me. Okay, so 420 times 2 pi divided by 60. What is it equal to? There is one more thing I need you to be careful with. Once you're pressing or plugging these numbers into a calculator, it will give you a digit here, let's say, or a number. But you might see, for example, as you can tell here, we have pi's in options here. So what do? My best recommendation, remember, try to convert these pi's into digits. So 7 times pi, what would that equal to? Once again, let's do this. Every pi is 3.14, yes? Or you could just press that in the calculator and that'll be it. So 7 pi's, that is 21.99. It's about 22, we can say. Let's just say 22, this one, by rounding though. 14 pi, what is it equal to? That is equal to 43.98, which is, let's just write this one the same as it is. Which is, we can, yes, 0.98 in here. And these are digits as well. So let's do this number. 420 times 2 pi divided by 60, right? Okay, see what we get. 420, are you doing that too? Well done. 2 pi times 2 pi, and then you can press equal just to make it easier, then divide by 60. And then, of course, you're going to get 43.98. Well done. That is option B here. Excellent. This is how you can easily do this. If the calculator gives, I don't know, actually no, just do this way would be way easier. And I believe you can tell what is this, the rate of change of angular displacement. That is, again, it is angular speed. We have another question. It says, how do we distinguish, make a difference between linear speed and angular speed? And at this point, just telling their definition would be, and their unit would be more than just enough. We said linear speed is clearly the change in displacement divided by the time. What it was measured in? Meter per second. But what about the definition of angular speed in here? We said there were two definitions. The time rate of, or you can say the rate at which a body rotates about some axis. That was one of the definition. The other definition was the time rate of change of angular displacement, right? And then for angular, let's say for angular speed, it was measured in radian per second. Well done. Okay, now there is another question here. It says what? More question actually. Says that this guy spins on a stool in a counterclockwise rotation. We've learned that if it is counterclockwise rotation, counterclockwise, all right, rotation, let's say counterclockwise direction on an object, we said arc length is positive, angular displacement positive, and then angular speed is also positive. Very good. Says clockwise direction, counterclockwise direction, with an average angular speed. So this is omega. It is 4 radian per second. In what time interval? Are they asking for delta t? Yes. Well, this guy's feet have an angular displacement that is delta theta of 8 pi radian. And these are all positive. So once again, because we have angular speed now, we're just going to write this. Omega, or angular speed, it is equal to delta, or angular displacement, divided by what? Delta t, or the time here. So we want the time. So would you like to rearrange the equation? Of course you should, right? That is delta theta divided by angular speed in here. Angular displacement by angular speed. What is the angular displacement? It says that is 8 pi. Okay, and then what about the angular speed in here? It says it is 4 radian per second. So in this case, of course, it's just 8 divided by 8 pi, okay? divide by 4, that is going to be 2 pi. Okay, so but that's a bit odd. You might see 2 pi as a unit of, let's say, as a number or as a magnitude for second. It is totally fine to say 2 times each pi is 3.14, yes? That is going to be 2 times 3.14, and that is going to be a total of 6.28 seconds. That is basically the time, okay, for this question here. All right. That was easy, I guess. Okay, the next thing that we have, by the way, you might say, what about, why is it written 6.3 here? We said that is 6.28, right? If you round this one up, of course, you can see that that would be 6.3 seconds, which makes no difference. And normally in Wizari, they won't give you like 6.28 and 6.3 at the same time. No, the numbers, of course, will be different, far from one another, so that you can clearly make a difference between the two. Okay, now there is another question here, which these questions are super easy, by the way, and I hope you practice them well enough so that it becomes easy to you too. It says a car tire rotates with an average angular speed. So here's an average angular speed. It is 29 radian per second. That is the first thing. And then it says, in what time interval, so delta t, it is unknown, will the tire rotate 3.5 times? Now, that is a keyword, and I need you to underline this for yourself. So here we have, watch this. So here is, let's say, a tire. Look, if this is the tire, how many times is going to rotate? Watch this. So if it starts at this point here, if it is going to, for example, move from this point here and then make one full rotation, isn't that one rev? So one rotation is the same as one rev, right? What if it is 2 rotation? That is 2 rev. What if it is 3 rotation? That is 3 rev, right? And then the last time it is going to be half a rotation as well. So it is going to be 3.5 times, or it's going to rotate 3.5 times. Remember, every time it rotates, that is 1 rev. So now we can say 3.5 rotation, it is the same as 3.5 revs. And don't forget, this is delta or angular displacement. Okay, so the question says what? Find the time. Good. So we'll say angular speed here, that is equal to angular displacement divide by the time, and then delta t, it is equal to angular displacement over angular speed, and then we said angular displacement, it is 3.5 revs. Don't forget, divide by omega, which is 29. But before you say it, can we use rev in calculation? No. But I just wanted to write it here because it might be easier to see how we can convert at this point. Every rev is 2 pi radian. So 3.5 times 2 pi and then divided by 29, you will get the time, which is going to be about 0.76 seconds. And that is the answer there. Okay, you double check for yourself too. All right, now there are more Wizari questions, of course. It says a car tire rotates with an average angular speed of this much. Let's say in 1 second, the tire will make dash rotation. Don't forget, they don't want, let's say, the angle in theta. After you find delta theta, you'll have to convert this to what? To revs in here. So let's do this one. Once again, angular speed, it is the arc, I keep saying arc length here. It is the angular displacement divided by the delta time, right? So now it says, here's the angular speed and here's the time, yes? So we are required to find the angle delta theta. So once again, we can say delta theta, if you cross multiply, that is angular speed times the time, yes? What is the angular speed? That is 22 radian per second. There is no conversion needed. What is the time here? Just 1 second. That'll be 22 radian, but that is not what we want. The question says how many revs that would be. And how do you convert radian to revs? Simply just by dividing by 2 pi then you will get the answer in revs. Let's get a calculator, or bring the calculator up and see how it is, or what it is. 22 divided by 2 pi. The answer is going to be 3.5. Do we have 3.5? Yes. So it is going to be 3.5 times here, or rotation here. Every rev that is considered as one full rotation. All right, there's another question which is similar to what we have just solved here. So I would let you give it a try, and you can try those as well. All right, one more question here. It says fill in the unknown quantities in the following table. I think this is pretty easy as well, just the same as the other one, remember. Okay, so what are we required to do? Fill in the table, and that's it. Okay, so what do we do if the numbers are not in the units that we want? Convert them. Simple. Okay, so here, what is unknown? The angular speed is unknown. So how do you find angular speed? Well, for part A, we could just say, okay, for part A, let me just write it here. Angular speed, it is equal to angular displacement over the time, and that is as simple as this. Do we have angular displacement and delta t? Yes, so just divide them, you will find the answer. That is for A here. Okay, what about the second one? This one is delta theta is missing. So once again, you could cross multiply from this equation. So delta theta would equal to angular speed times the time. Once again, you have this and this, multiply, then you will get the answer right here. But if you look at C, just like the other table we had, it is a bit interesting because the requirement is different here. What is it different here? As you can see, it says find the angular speed, but angular displacement, it is given in revs. Can we use revs in calculation? Well done. So at this point, C, right, it is equal to what? Angular speed, it is equal to angular displacement over the time. But what is the angular displacement given? It is negative 1.2 revs. I'll just write rev for now, and then divided by 1.2. And we said we cannot use rev, but every rev, it is equal to what? It is equal to 2 pi radians. Okay, now, simple, I believe. So there's no negative in here. So 1.2 cancels out with 1.2. So angular speed is going to be negative 2 pi radian. And of course, it's going to be per second here, right? Like you could just write the second for the time here. If not, you could just say negative 2 times 3.14, that is fine. If not, you could just say negative, that is going to be 6.28, which you can, of course, round it up to negative 6.3 as well. That is radian per second. So this is how you can get the answer correctly. And then part D, of course, I think that you think that is easy enough, right? It says find delta t. So what is delta t equal to? First start with the angular speed. It is delta theta over delta ts. And if you want delta t, you could just switch their places here. Delta t, it is equal to delta theta over angular speed. And then just plug in the numbers, you can find the answer. Do we have to convert anything? No, because these numbers are already in the units that they're supposed to be. All right, and you can see Wazadi questions here as well. All right, but then you can see that there's this question here, it's been in Wazadi. It is also one of the chapter review questions as well. This is something very important, and I need you to focus at this point very well. Okay, so what does it say? It says a bicyclist, a person rides, let's say a bicycle, of course, along a circular track. So there's circular motion. If the bicyclist traveled around exactly half of the track. So what does it mean, half of a track? We know that this is the cycle, or one full cycle. This is the track of which is a circle, right? If the person or the bicyclist is traveling half of the track, what does it mean, half of a track? Can I say it is half a rev? Because that is half of a track, right? So half a track here, that means half a rev. Half of a rev, you could say. In other words, we can say 1/2 of a rev here. That is what it means. Or when they say half a track, that is what it means here. That means half of one full revolution. 1/2 of a rev or 0.5 rev makes no difference. This is how much they travel, but it says in what? In 10 seconds. So this is delta t. Don't forget, this is delta theta, okay? Which is half a rev or 1/2 of a rev. The question says, what is the average angular speed for the bicyclist here? So that is easy, of course, as well, just like the other ones here. But before that, let's just, not this one. Okay, let me do something perhaps a bit new. And that is this one here. So let's say this is what we want, or that is what we're trying to do here. Just zoom in this a bit. Okay, so we said half a track, so we can say delta theta. It is going to be half a rev, don't forget. Okay, and then what about the time? The time is given is 10 seconds. What is the question asking? It says, what is the average angular speed? Okay, so now of course we know that average angular speed, it is equal to what? Average angular speed, it is equal to delta or angular displacement divided by the time. Very good. But once again, we said half a track, that means 1/2 of a rev divided by 10 seconds. But can we use revs in calculation? No, but we know that every rev, it is equal to 2 pi radian. So you can use this instead. So now once you do the math, you can say this 2 cancels out. So it is going to be pi over 10. Pi over 10. And we know that pi over 10, it is clearly 3.14, all right, over 10. That the answer is going to be 0.314. This is angular speed, don't forget our average. So it is going to be radian per second. This is how you do. Sorry about this. This is how you do this one correctly. Okay, now let me switch or perhaps make a few changes regarding this question. Now at this point the question says if the bicyclists travel half of a track, and you can see here. What if the question say the bicyclist is traveling, let's say, 1/4 of a track? 1/4, that would be 1/4 of a cycle, and that is the same as if you say 1/4 of a rev. What if the question say makes 2 full cycles? So that would be 2 rev. What if the question says 3/4 of a cycle? 3/4 of a cycle, that is going to be 3. What did I say? 3/4? Yes. If it says 3/4, then of course we can say 3/4. Let me just get the other one back. If it says 3/4 here, not yet. Okay. What is wrong? Okay. Let's just go back to. Okay. So that is basically what we have. What if it says like 3/4 of a track? So in that case, of course, we could have said 3/4 rev, don't forget. So whatever the number they say, use that wisely, and that'll be the angular displacement here. All right, now moving next. Okay, here you can see that there's another question which is very similar. The only thing that has changed, but by the way, I think I didn't answer the question yet though. All right, so now let's go back. I did actually, right? It was 0.34. So that is the correct answer. Now remember. Okay, and then moving forward, says a bicyclists ride along a circular track. If the bicycle traveled around exactly half of the track, but this time in 20 seconds, doesn't make any difference in terms of the procedure or the steps? No. But of course, the time is here different. Now, take a look at this one. It says a bicyclist or a bicycle driver is moving in a circular track if he cuts a quarter or 1/4 of the path in 10 seconds. Quarter of a track, isn't that 1/4 of a rev? Yes. In what time? So this is delta theta. In what time? In a time of 10 seconds. So what is the average angular speed? You will do the same thing. And this is, of course, after doing this, you can get the correct answer here. Okay, now I believe we'll end this session here. Next time, inshallah, we'll talk about the angular speed for some of the things that are constant, like for those things that are moving in a circle at a constant speed, for those objects, they're not going to speed up or slow down, which I believe is going to be interesting. But before letting you go, of course, or end the session, I would like to give you a quick review of or summary of what we studied today or what we went through today. The first thing we went through was angular displacement. We said it is the angle through which a point, a line, an object, it is, let's say, moving in a specified direction around a specified axis. And how did we use to measure angular displacement? We said it is the arc length divided by the radius. Angular displacement is a vector quantity. That means it can be positive or negative. If the rotation is clockwise, arc length and angular displacement are negative. If the rotation is counterclockwise, then arc length and the angular displacement are both positive. And then after that, we've learned about angular speed. We said angular speed, it is the rate at which a body, or let's say the time rate let's say the rotation of an object. Let me just say that properly. Okay, the rate at which a body rotates about an object, that's one way. The other way, we said it is the time rate of change of angular displacement. Angular speed clearly also is a vector quantity. If the rotation is clockwise, it is negative. If the rotation is counterclockwise, it is positive. For both angular displacement and angular speed, they must be in appropriate units so that we can use them in calculation. Like for angular displacement, it must be in radian. What do we do if it is not in radian? You have to convert. We'll do the same thing for angular speed. If it is not in radian per second, we'll have to convert to radian per second. Then after that, we can use them in calculations. Stay for more videos. Until then, keep practicing, and I'll see you soon, inshallah. Assalamu alaikum wa rahmatullah.